This chapter is a continuation of Chapter 2, creating a REST API application, which is part of the standard path of this course. There's also a bonus NoSQL MongoDB chapter that begins right where Chapter 2 left off as well. If you want to code along through both of these database chapters, make sure you save your progress from this last chapter into a separate branch. This way you can use it later for the MongoDB bonus chapter. If you're using Git, make sure to create a new branch to store your current progress and then head back to your master branch to continue along with this Postgres and TypeORM chapter as well as the rest of the course. By fracturing these SQL and NoSQL sections, you can easily choose and watch whichever section you need for your project or code along through both. Docker is a platform for developers to build, run, and share applications that are within containers. The use of containers to deploy applications is called containerization. Containerization has become increasingly popular over the years due to many benefits they bring to the development process. Let's go over a few key benefits. Containers are flexible, lightweight, portable, meaning you can build them locally, deploy to the cloud, and run anywhere, and loosely coupled. This means that containers are highly self-sufficient and encapsulated, allowing them to be replaced or upgraded without disrupting any other containers. There are many other great benefits to containerization in Docker, but hopefully you get the idea so far. Fundamentally, a container is just a running process with some added encapsulation features applied to it. This helps keep the container isolated from the host and other containers. In this course, we'll be using Docker to set up a database locally on our machine. If you do not have Docker installed already, go ahead and pause the video and check out installations instructions on the official docker.com website. In addition to Docker, we'll be utilizing Docker Compose. Docker Compose is a tool for defining and running multiple container Docker applications. With Docker Compose, we can use a YAML file to configure our application services. If you're not familiar with YAML, don't worry, we'll briefly cover how we'll be setting up the file, but it's nothing too intimidating. Once we have all of these things set up, with just a single command, we can create and start all the services from our configuration on any machine. Docker is going to make working with our application that much simpler in the future, not just for us, but also for other developers, different machines, and can even help us quickly set up our application in the cloud. For Mac and Windows users, Docker Compose is included out of the box with Docker. But if you're on Linux, there are a few additional steps you'll need to do in order to get Docker Compose installed. So make sure to check the Docker Compose documentation for more information, or check the link below in the lesson description. Now that we have Docker installed, just make sure that it is running on your machine and let's see it in action. Previously in our application, we were using a mock data resource in our Coffee service. Let's take it up a notch and use a real database so we can really take our application to the next level. We're going to be using PostgreSQL because not only is it one of the most performant, feature-filled database management systems out there, but it's also free. In the past, we may have gone to the Postgres website, installed the database locally on our machines, but let's take advantage of Docker to handle all of this for us. We're going to be using the Docker Compose tool and its YAML configuration to set everything up that our application needs. To get started, let's create a docker-compose.yml file in the project's root directory. Next, let's define a database container in YAML format. YAML is an interesting configuration file in that spacing, indentation, and dashes all matter and do something. If you want to learn more about YAML, please check out yaml.org. There's a lot going on here. If you look down below the course video, you'll be able to copy what you need for this file. The most important pieces here are that we have a DB service that is using the Docker image of Postgres. A Docker image is a multi-layered file that will execute code within a Docker container, and in this case, it will be creating a PostgreSQL database. Next up, we have ports. We can see that we'll be using the default ports for PostgreSQL of 5432, but notice the colon and then the same port 5432 again. This indicates to Docker that internally within the container, it should have the database set up on port 5432, but also have it accessible outside of Docker on the same port as well. This lets us be able to access this database that's inside of the Docker container, outside of the container, and on our current machine. Lastly, we're setting up a password for Postgres, which we've made pass123. I know a lot of this might seem like a lot, but with all that in place, we can use the Docker Compose CLI to run the database service effortlessly with just one command. In our terminal, let's enter docker-compose up-d to bring our Docker container up. The -d flag means that we want to run our containers in detached mode, meaning that they are going to be running in the background. We only have one service listed in our Docker Compose YAML file, but for future reference, if you had other services here and wanted to run a specific one, you can pass the name of the service you want to run by entering the name of it. Just remember that when you pass in nothing, Docker Compose will spawn all the services defined. Nest itself is database agnostic, allowing you to easily integrate with any SQL or NoSQL database of your choice. There are a lot of different ways you can integrate Nest with databases, and they all depend on your personal preferences or project's needs. For this chapter, we'll be using the popular, mature, and fully featured Object Relational Mapper, or ORM, known as TypeORM. TypeORM will let us interact with entities in our database in a type-safe and incredibly simple manner, letting us get things done faster than ever. In this course, we'll be setting up TypeORM with the Postgres database that we have up and running in our Docker container, but TypeORM provides support for many other relational databases, such as MySQL, Microsoft SQL Server, SQLite, and even NoSQL databases like MongoDB. So use whatever suits your projects best. To get started with TypeORM, let's get the necessary dependencies installed for our application. We're going to be continuing ahead as we already have these installed, but if you're following along, just pause the video and come back when it's finished. Note that the procedures we walk through in this chapter will be the same for pretty much any database supported by TypeORM. Alright, so we can see we've installed a Nest.js TypeORM package, TypeORM itself, and also PG, which we need since we'll be using Postgres in our application. Once the installation process is complete, let's get TypeORM set up in our I Love Coffee application. Let's open up our app module TS file and head over to the imports array. Nest.js comes with a module that helps make the TypeORM integration extremely simple. To get started with this module, let's import the TypeORM module from the Nest.js/TypeORM package and add it into our imports array here. We need to initialize this module, so let's call the forRoot method on the TypeORM module, which lets us configure the connection to TypeORM, as well as a few additional tools available to integrate it with Nest. Let's break everything down so it all makes sense. Let's start out with the type, which we've set to Postgres since we know we're using PostgreSQL. Our host will be localhost since we're developing locally. Port is 5432, which is what we set in our Docker Compose file. Username is a username for accessing our database. We never set one in our Docker Compose file. We're going to use Postgres, which is the default for PostgreSQL databases. Password we've set to pass123, just like we did in our Docker Compose file again. For database here, we'll list the name of our database that our application will be using. Let's call it Postgres. Autoload entities, let's set this to true. This helps load modules automatically instead of specifying the entities array. We'll dive deeper into this later in an entities section. Lastly, we set synchronize to true. Synchronize ensures that our TypeORM entities will be synced with the database every time we run our application. This is great for development, but a very important tip, make sure you disable this when you're in production. Now that we have TypeORM configured, let's open up our terminal and start our application to make sure everything's working. Let's fire up the application in development mode again with npm run start:dev. If we look carefully, we should see TypeORM modules dependencies initialized, meaning we have successfully established a connection to our Docker Postgres database. If you're having any issues setting up TypeORM, Make sure that Docker is running with Docker compose up-d. Also, make sure the password inside your TypeORM module for root matches what you have in your Docker compose file. An entity represents a relationship between a TypeScript class and a database table. So in the case of our Nest applications, our entities will be classes decorated with the entity decorator. In the previous lesson on TypeORM, we set synchronize to true in our TypeORM for root configuration method. This synchronized configuration lets TypeORM automatically generate a SQL table from all classes with the entity decorator and the metadata they contain. This automatic synchronization saves us a lot of manual coding that we'd have to do otherwise while actively developing our applications. Remember, this is designed for development only. Make sure to always disable this feature in production. Let's get started and update our existing mock coffee entity and set it up with TypeORM. Let's start by opening up our coffee entity and adding this new entity decorator on top, making sure to import it from TypeORM. As we mentioned a moment ago, each entity class represents a SQL table. By default, TypeORM will name the SQL table based on our class name in lowercase. So in this example, the SQL table that will be generated will be coffee in lowercase. If you want to use a different table name for your entity, you can specify inside of the entity decorator. Passing the string coffees into the decorator will generate a coffees table instead. Let's remove this and just use our class name coffee as the SQL table for now. Now that we have all this in place, we can start defining the columns in our table. Every property in our class that is annotated with the column decorator will be mapped to a table column. Let's build out our coffee entity to see all of this in action. First, almost every table needs a primary key, right? Let's use a new decorator called primary generated column and decorate this ID property with it. This decorator will not only define ID here as the primary column, but also auto-increment the value for us. Next, let's add the column decorator to all the rest of our properties here: name, brand, and flavors. For flavors, we need to do something a little bit different since this is an array, and we want to make our flavors optional as well. Inside of the column decorator, let's pass in two arguments, one that labels this column as type JSON, and the other an object with nullable true. With this in place, TypeORM now knows that flavors should store arrays as JSON and to make this column optional in our table. We set this column to JSON here, but this is just temporary. Soon we'll show relationships in a coming chapter. Note that each column here is not nullable, meaning required by default. So in our coffee entity, all of the columns besides flavors are required. Now that we have the basics of our entity set up, let's register this coffee entity in our application. Now that our application is a bit modularized and we're dealing with this entity inside of the coffee module, we need to make TypeORM aware of the entity inside of this child module itself. To achieve this, let's open up our coffees module and first create an imports array inside of the module decorator. In this imports array, let's add TypeORM.forFeature, passing an array with our coffee entity inside of it. The use of forFeature here registers TypeORM in this child module. Remember, we used forRoot in our main app module before, but we only do that once. Every other module will use forFeature when registering entities. Inside of the forFeature here, we pass in an array of entities, but in our case, we only have one, our coffee entity. If you look at the coffee table now in the database UI of your choice, it should look something like this and have everything set up just as we created it. TypeORM supports the repository design pattern. This means that each entity we create has its own repository. The repository class available from TypeORM acts as an abstraction over our data source and exposes a variety of useful methods to interact with the records stored in our database. Since we've already registered coffee entity in the scope of our coffee module, we now have the ability to inject the automatically generated repository into our coffee service using the inject repository decorator exported from nest.js/TypeORM package. Previously in our coffee service, we used the coffees array as our mock in-memory data source. Since we're using a real database now, We no longer need this mock implementation, so let's remove it. Let's go inside each method one by one, replacing our mock data interactions, and use our new coffee repository. Before we dive into everything here, note that we will be using a JavaScript feature called async await. If you aren't familiar with it, async await makes promises easier to manage and much more readable. We'll need to update most of our methods here to be async in order for this to work. Let's start things off by looking at the findAll method. Let's remove the current code inside the method and try to use our new coffee repository. Let's add return this.coffee repository and hit period to see what kind of methods are available to us from this TypeORM repository. As we can see, there is a vast variety of methods available to us to handle almost any interaction with our data. We need to find all coffees. So in our case, let's use the find method here. Next, let's update find1. First, let's add async before the method name. Inside the method, let's replace the existing mock code and use the repository method find1, making sure to pass in the ID. Since find1 here returns a promise, let's await the result. Next, our create method. Let's replace the old code with the following and break it down line by line. The first thing we need to do for this method is to create a coffee class instance based on our partial DTO and save it to the variable coffee. Now that we have an instance of coffee created, all we need to do is call the save method, which returns a promise, and our new entity will be saved to the database. Also, let's make sure to replace createCoffeeDTO of type any with the appropriate type createCoffeeDTO, which will now give us full type safety here as well. Now on to update. First, let's add async again before the method name, and let's replace the existing code with the following. Let's break everything down line by line again so we understand everything that's happening here. First, we're using a new repository method called preload. This method creates a new entity based on the object passed into it. Preload first looks to see if an entity already exists in the database, and if so, retrieves it and everything related to it. If an entity exists already, preload replaces all of the values with the new ones passed in here in our update coffee DTO. Note the preload method will return undefined if the ID of the entity passed in was not found in the database. For this reason, let's make sure we always test whether the result is undefined, and if so, you can see we're throwing a not found exception here. To finish everything off, let's make sure we save our changes to the database by calling the repository save method. Just like we did in our create method a moment ago, we can also replace that type any in the parameters to use our update coffee DTO, making us fully type safe here as well. And that's it for our update method. Next up, we have the remove method. Let's replace the existing code with the following and break it down. We need to retrieve the coffee, and if it exists, remove it from the database. To achieve this, we can call the find1 method that's within this service, passing in the ID. Once we have the entity, all we need to do is call the repository remove method, which returns a promise, and make sure we pass in the coffee entity we just received. We don't need to throw any errors manually if coffee does not exist, because the find1 method in our service automatically handles that for us. And just like that, with a few lines of code in our service, we've set up an entire CRUD workflow for our coffee entity. We've managed to quickly migrate all of our methods to use our real database now too. Let's fire up Insomnia and test some of these routes to make sure everything works. Let's start by making a few post requests to populate some entries in the coffee table. Make sure to change a property or two in each request payload so they're all slightly different in the database. Now that we have a few entries in our table, let's make a GET request to /coffees and see if we get data back from the database. Great, everything works so far. Next, let's test the patch endpoint and update the first coffee with ID 1. Let's change the endpoint we want to hit to coffee/1. And for our body payload, let's pass in an object with a different name. In our case, we're going to update the name to Coffee Updated. Once we hit send, we should see it worked. Our patch endpoint actually returned the newly updated entity back from the database for us. Let's make sure it really did make those changes by making a GET request for coffee/1 to double check. Perfect, we can see it really did update the name for that coffee. Lastly, let's make sure delete works by removing this item from the database. If we switch Insomnia to make a delete request for the same ID of 1, once we push send, we should see that everything looks okay. No errors. So far so good. But let's do one more GET request to make sure that it's really gone. When we push send, we should see a 404 not found message come back. It worked. The item is really gone now. So just like that, we have everything working perfectly. We're using a real database now, and we've managed to hit a lot of fundamental aspects of TypeORM and integrating it with our Nest applications. Our app is really starting to take shape now. Relations are associations between two or more tables based on common fields from each table, often involving primary and foreign keys. There are 3 types of relations. The first are one-to-one relations. In these relations, every row in the primary table has one and only one associated row in the foreign table. In TypeORM, we define these types of relations with the one-to-one decorator. Next are one-to-many or many-to-one relations. For these relations, every row in the primary table has one or more related rows in the foreign table. In TypeORM, we define these types of relations with the one-to-many and many-to-one decorators. Lastly, we have many-to-many relations. This is when every row in the primary table has many related rows in the foreign table, and every record in the foreign table has many related rows in the primary table. In TypeORM, we define these types of relations with the many-to-many decorator. In a previous lesson, we temporarily labeled flavors as type JSON so we could store an array there. Let's fix this now to use relations and point to multiple entries in a new flavor table we'll create in a moment. To get started, let's create a new flavor entity with the Nest CLI, making sure we put it within our coffees domain in the coffee/entities folder. In our terminals, let's enter in nest g-class coffees/entities/flavor.entity --no-spec. Just a reminder that we're passing in the no-spec flag again so that the CLI doesn't generate a test file, as we won't need them for entities. Now let's open up our newly generated file and define the corresponding columns. Also, and this one is important, let's make sure that the name of our class is flavor without the entity suffix, as we don't want the word entity for our database table name. For our flavor entity, we want to keep it simple, as we only need 2 columns, ID and name. With this in place, we can now define our first relation. Let's jump over to our coffee entity and update our existing flavors property, removing the column decorator, and introduce some other decorators we'll need to make this a relation. First, let's introduce a new decorator called join table from the TypeORM package, and add it on top of our flavors property. This join table decorator helps specify the owner side of the relationship, which in this case is the coffee entity. Now that we've joined these tables, let's define the type of relationship that we want to exist between these entities and use the corresponding decorator. In this case, we need to define that each coffee can have multiple flavors, so we're going to be using many-to-many decorator here for this relation. Let's add the many-to-many decorator, also from the TypeORM package, right below join table, and pass in a few parameters to help this decorator understand and establish this relation for each side. For our first parameter, we want to establish what the type for the relation is by entering type flavor. This is just a function that returns a reference to the related entity, in this case the flavor entity. For the next parameter, let's pass in an arrow function that returns the related entity and specify what property needs to be selected that is the inverse side of the relationship. In other words, what is coffee inside of the flavor entity? In our flavor entity, we will reference coffee as the coffees property. So we want to select it here via flavor.coffees. You may see we're getting some errors here as the coffees property does not exist on our flavor entity yet, but we'll fix that in a moment. Let's jump into our flavor entity and set up the inverse side of our many-to-many relation. Let's add that missing property called coffees to our flavor entity and give it the type of coffee array. Our many-to-many relation was created by the owner, coffee, but we need to make sure TypeORM is aware of the inverse side of the relationship in this flavor entity in order for this to be properly connected. Since coffee is the owner in this relationship, we don't have to use the join table decorator again. Just as we did a moment ago, let's add the many-to-many decorator on top of the coffees property here and pass in a few parameters. First, let's declare what the type of our inverse entity relation is. In this case, it's coffee. As for the next parameter, let's select where flavor is indicated on the coffee entity, which is the flavors property. So let's enter in coffee.flavors here. Great. And just like that, we've created a many-to-many relationship between these two entities. But we almost forgot one thing. We need to make sure we register our flavor entity with TypeORM. Let's add flavors to the TypeORM.forFeatureArray in our coffees module. And that's it. Once we start our application, the following tables will be created by TypeORM. Note that when we run our application in development mode, TypeORM will automatically add these tables for us. This is due to synchronize true being set. But once again, make sure to disable this for production. In the previous lesson, we removed the flavors JSON column, including all of its data, and created a relation, which now gives us a total of 3 tables in our database. Coffee, which represents coffees, flavor, which represents flavors, and coffee flavors flavor, which represents the coffee flavor many-to-many relation. So now that we have set up our relation in the previous lesson, how can we make sure our endpoints retrieve all dissociated data? Our get/coffees endpoint currently returns a list of entities, but without the flavor relations we've associated with it. Even though we define the relationship coffee with flavors, the flavor field won't automatically be populated in our response. But why? This is because relations are not eagerly loaded by default. We have to explicitly specify what relations we want to be resolved when calling the find method of the repository. To fix this, let's open up our coffee service and update our 2 get endpoint handlers to include this relation and make sure flavors gets populated. Let's start with the findAll method. TypeORM allows us to pass in many different conditions or options to the repository methods. If we go to definition on the find, for example, you can see all the different options for every one of the methods available to repository. Let's dive in a little deeper and see what find many options are. In this interface, we can see we're able to pass in things like skip or take, which we'll be using later for pagination. But it looks like this interface is extending another one. Let's keep digging and see what find one options contains. In here, we have a lot of common database operations for things like join, where, order, etc. In our case, we're looking for relations, which we can see as an array of strings. Perfect. Let's go back to our coffee service and use it. Let's pass this findOptions object into our find method, entering in relations with an array with the string flavors inside of it. We're passing in flavors here since we've labeled that column as our relation for coffee. Great. Now let's update our findOneGet method to make sure it's using relations and populating flavors as well. Inside our findOne, let's pass in a second parameter after ID and pass in the same thing. An object with relations that's a string of flavors. Let's save our changes, head to Insomnia, and call the findAllGetEndpoint/coffees once again and see if it works. As you can see, each object now contains the resolved flavors relation. Excellent. One last thing, let's test the findOneGetEndpoint by checking coffees/2 for example. And great, it works as well. And just like that, we're all set. Let's imagine a fairly common scenario where we want to add a new coffee into our database, but it has flavors that are not present in our flavors table just yet. Luckily, we have a few options we can do to handle this properly. We could manually insert all of these new flavors into the database and afterwards create a new coffee entity, but that's not ideal. A better option would be for us to do cascading inserts. To enable cascading for both inserts and updates, let's set the cascade property to true inside of our relations, such as the many-to-many relation we have between coffee and flavor. Note that if we want, we can also limit cascades to just insert or update as well. With this small addition, flavors that belong to a newly created coffee will be automatically inserted into the database for us. But to make this work, we still need to perform a few more updates to our code. If we look back at one of our DTOs we've made so far, they contain a flavors property, which is an array of strings. But we need to make sure we map these strings, which are names of flavors, to real entities, instances of a flavor entity. To do this, we'll first need to inject the flavor repository into our coffee service class. With this in place, let's define a new private method and call it preloadFlavor by name. In this method, we're taking a flavor name as an input argument and returning a promise that resolves to a real flavor entity. If a flavor with the specified name already exists in our database, we want to return it. Otherwise, this method creates a new class instance with the name we passed in. Now that we have this method, let's put it to good use in both our create and update methods. First, let's make a few tweaks to the create method. This method needs to loop through all the flavors in our createCoffee DTO with the map function and call our new preloadFlavor by name method to make sure they're properly populated. Using await in combination with promise.all lets us wait until the entire array of promises finishes before executing further code. Once this code finishes executing, we'll have an array of flavor entities in our new flavors variable we just defined here. Now all we have to do is merge createCoffee DTO with our updated flavor entities. We can easily do this by using the spread operator to get all the properties of our createCoffee DTO object, and then afterwards overriding the flavors property with our new populated flavors variable of the same name. You can see we're getting some errors here as the flavors type doesn't match. Let's fix this real quick. If we head over to our coffee entity, let's change the type of the flavors property to the type array of flavor, which going forward is what we'd always want to do when creating entity relations. With this in place, we can now go back to our coffee's create method. Now, all we need to do is call the save method for our new coffee, and that's it. Likewise, we must follow the same steps in our update method below. There's one difference here that we should point out. In our patch operation, the flavors property is optional. Let's make sure we add an inline condition here to make sure we actually have flavors before we call the map method on each one of them to preload it. If we didn't add this condition, we'd get an error if flavors was ever undefined. Now heading back to our coffee entity, since we have cascade set to true in our relation, any new flavors will be automatically added to the database together along with any coffees created, with everything and their relationships tied together. Let's fire up Insomnia and test some of these routes to make sure everything we did works. First, let's make a post request, making sure we specified a flavors property in the request payload and hit send. Great, no errors. Now let's make a get/coffees request to see if these new flavors were properly populated in our database. Great, there we have it. We can see the new flavors were added into the database and even came back with this response. In previous lessons, we set up our get endpoints to take in pagination parameters, but we didn't actually implement anything, especially within the context of TypeORM. Let's take a look at how we can apply limit and offset in our coffee service findAll method to retrieve the specific amount and specific selection of coffees from our database. First, let's generate a class for our pagination query DTO, which we haven't made yet because our pagination query was just for demonstration purposes so far. Using the Nest CLI, let's create this DTO by entering nest g class common/dto/pagination-query.dto -- Note that we're generating this class in a new directory named common. Going forward, we're going to keep things that aren't tied to any specific domain and could be reused by multiple controllers in this common folder. Let's open up this new pagination query DTO and set two properties, limit and offset, both of which we can make type number. Now, let's add a few decorators to both of these properties. The first one being the type decorator from the class transformer package. On this line, we're making sure that the value coming in is parsed as a number. You might remember from previous lessons we said that query params are sent through the network as strings. This helps solve that problem automatically for us. The next decorator we'll use is called isOptional from class-validator. As the name implies, this decorator marks this property as optional, meaning that no errors will be thrown if it's missing or undefined. And lastly, let's add the isPositive decorator, also from class-validator, which checks if the value is a positive number greater than 0. One thing to remember about the type decorator we added here is that instead of manually doing the conversion here like we did in this file, we could have alternatively enabled the implicit type conversion on a global level by adding the transform options object to our validation pipe with enable implicit conversion set to true. With this option set in our validation pipe, we no longer have to explicitly specify types with the type decorator. So let's use this and remove that type decorator from our pagination DTO. Now that we have all of that in place, let's navigate to the coffees controller and give that pagination query parameter our new DTO type pagination query DTO in the findAll method signature. Next, let's make sure we're passing this pagination query argument to the findAll method since we'll need it for TypeORM. Let's jump into this findAll method in our coffees service and update the input arguments there as well. Great, so now we're using real DTOs and we're passing the limit and offset values down. Next, let's update our TypeORM repository find method to utilize everything. You may remember in previous lessons, we looked inside of the interface for the repository find method and saw all the conditions or options we're able to pass to TypeORM. For pagination, we saw that they're called skip and take. Let's add both of these inside of our find conditions object, passing offset to skip and limit to take. And just like that, we've set up real pagination with our database. So let's open up Insomnia and test this out and see if it really works. Let's start by calling our coffees get endpoint, but this time let's make sure we pass in some query parameters. First, let's pass in !limit = 1 in our URL query. This should only return one result if everything goes well. Let's push send and try it out. Great, it worked. We received just one coffee back from our database. Now let's remove limit equals 1 and try $offset equals 1. When we push send, we should see now that it skipped the first coffee and we got back all the rest of the results from the database. Let's imagine that a new business requirement comes in for our application. The I Love Coffee product team wants users to have the ability to recommend different coffees, and whenever that occurs, we need to add a new event to the database that can be used later for data analytics purposes. To pull this off, we're going to need two things here. We have to provide a new endpoint that allows users to recommend coffees, and we're going to need to store the event after that previous call finishes. In order for this whole process to succeed, we need both operations to be successful. Otherwise, we might have inconsistencies in our database. This is where transactions come in. A database transaction symbolizes a unit of work performed within a database management system. Transactions are a reliable way to accomplish multiple tasks independent of other transactions. There are many different strategies to handle TypeORM transactions, but we recommend using the Query Runner class because it gives us full control over the transaction. Note that there are other complex and advanced techniques to achieve this, which leverage Nest scope providers and interceptors to automatically wrap every write query in the transaction. But we'll be covering those techniques in upcoming advanced Nest.js courses in the future. For now, let's keep it simple so we can conceptually understand everything first. Before we get started, let's create this new event entity that we'll use to signify events that occur in our application. Let's create this new entity with the CLI and put it in an events folder. In a real-world application, we'd want to create and wrap this entire domain in a Nest module so that everything pertaining to events, such as services, controllers, etc., are isolated. But for now, we'll skip that as we don't need it at the moment. Just a reminder that we've passed the no-spec flag here again, so that the CLI doesn't generate a test file as we don't need them for entities. Now let's open up our newly generated file and define some columns we need. Just an important reminder again, let's make sure that the name of our class is event without the entity suffix, as we don't want the word entity in our database table name. For our event entity, let's keep it simple and add a few basic columns: ID, type, name, and payload. Payload will be our generic column where we can store events payloads. There's nothing new here that we haven't already seen and used for most of the decorators in all of our lessons so far. Alright, so let's continue. Before we're able to use this entity, we have to add event to the TypeORM for feature entities array in our coffees module. Next, let's make sure we add this new recommendations property we talked about to our coffee entity. In our coffee entity, let's add an additional column calling it recommendations. Let's set the default value to 0 and make it of type number. Perfect. Now that we have our coffee and event entities all set up, let's get back to our coffee service and put everything together. In order to create transactions, we're going to use the connection object from TypeORM. Let's inject connection into our coffee service constructor the traditional way without any decorators, as they're not needed for it. Let's just pass in private read-only connection : connection. Great. Now let's use this connection object to create our first transaction. Let's get started by creating a new async method in our service and call it recommend coffee with one parameter, a coffee instance. Inside our method, we could see we're first creating a new query runner, then establishing a new connection to the database with this query runner. Once we have a connection established, we can start the transaction process. We want to wrap our entire transaction code in a try-catch finally just to make sure if anything goes wrong, our catch statement can roll back the entire transaction. Remember that we said in order for this to succeed, both operations have to be successful. Transactions give us the ability to roll back and undo anything that happened in case something goes wrong. Inside our try statement, we can see we're increasing the recommendations property on our coffee and creating a new recommend coffee event. Then we're using the query runner's entity manager to save both coffee and event entities. And we could see in our catch statement here, if anything goes wrong saving either entity, we're catching the error to prevent inconsistencies in our database by rolling back the entire transaction. Lastly, the finally statement here is used to make sure we release or close the query runner once everything is finished. And that's it. Just like that, we can create transaction statements that can help us achieve multiple actions to our database, ensuring they only happen if everything is successful. Indexes are special lookup tables that our database search engine can use to speed up data retrieval. Let's say that in our application, a very common search request will be retrieving an event based on its name. To help speed up this search, we can define an index on the name column using the index decorator. In more advanced cases, we may want to define composite indexes that contain multiple columns. We can do this by applying the index decorator to the event class itself and passing in an array of column names inside the decorator as an argument. Indexes can help give our application both rapid random lookups and efficient access of ordered records. Use them whenever performance is vitally important for a certain entity. Database migrations provide a way to incrementally update our database schema and keep it in sync with the application's data model, all while preserving existing data in our database. To generate, run, and revert migrations, TypeORM provides us with a dedicated CLI we can use. Migration classes are separate from our Nest application's source code. This is because their lifecycle is maintained by the TypeORM CLI. Since these migrations are outside of Nest, we're unfortunately unable to leverage dependency injection and other Nest-specific features for our database migrations. Before creating a new migration, we need to create a new TypeORM configuration file and set up our database connections properly. Let's start by creating an ormconfig.js file in the root directory of our project. These configuration settings here are all of the ports, passwords, etc. that we used from our Docker Compose file, with a few additional key values used to let TypeORM migrations know where our entities and migration files will be. TypeORM migrations need to work on compiled files, which Nest will output in the dist folder. With all this in place, we can create our first migration using the following command: npx typeorm migration :create -n, and let's name this migration Coffee Refactor. If you haven't seen npx before, it's a great utility that lets us use executable packages without having to install them. This lets us use the TypeORM CLI without actually installing it on our machine. So this command generated a new migration file for us within our source/migrations directory. In our application's code, let's create a scenario where our database requires a change so we can test out this entire migration process. Heading over to our coffee entity, let's imagine we had to do some refactoring here and we had to rename the existing name column to title. Making changes to our entity code will synchronize our local development database because we're using synchronize true, but it won't automatically update our production database schema, which is one of the main reasons why migrations come in incredibly handy. One thing to remember here is that when we make the change from name to title in our entity code, it will not only remove the name column, but all of the data in that column as well. Only after that column is removed does it create the new title column without any of the old data, which is now lost. Migrations help us rename the existing column and maintain all of our previous data. You can see why this is so important, especially when you're making changes to live production databases. Let's open up that migration file that we just created and add some migration logic to let our database know that we want to make some changes. Every migration should have an up and down method. Up is where we're going to instruct what needs to be changed and how, while the down method is where we're going to undo or roll back any of those changes. Down is extremely important just in case an issue comes up from our migration. We need to have an exit strategy to help us undo everything. So let's add some code here in the up method to instruct what we need done. As you can see, we're going to use the query runner query method to make our migration changes. The changes in this case are to alter table coffee and rename the column name to title. This was of course just our example use case, but you could do any kind of database migration you need here. As we said, we also have to provide logic for how our migration can be rolled back in the future. So in our imaginary scenario here, let's say we needed to revert that title column back to name. Now that we've finished creating our migration, let's run it and see if it works. But first, we need to make sure we build our source code so that TypeORM CLI can find our entities and migration files in our dist folder. So in our terminals, let's first run npm run build. When our build finishes, everything will be compiled into our dist folder. Now we can run the TypeORM migration command via npx TypeORM migration:run. And as we can see in the console, our newly created migration has been executed successfully. If we try to execute this command again, we'll see the following message. No migrations are pending, which is great. That means there's nothing more to do. For testing purposes, let's revert our changes back so our column is name again. Let's enter in npx TypeORM migration:revert. Again, as you can see in the console, our migration has been successfully reverted. Since we did all of this merely for example's sake, let's make sure to go back and revert that column in our coffee entity to name again, before we forget. As another option for migrations, the TypeORM CLI is also capable of generating migrations automatically. It connects to the database and compares existing tables with entity definitions you provide. If there are any differences found, TypeORM generates a new migration for us. Let's try this out and add a new column here, for example description, with nullable set to true. Just like we did before, let's compile our code again using npm run build. Now let's let TypeORM generate a migration for us by entering npx TypeORM migration:generate -n, and let's name it schema sync this time. This command will generate a migration for us that should add this new description column. When it's finished, let's open up this file and check to see if it looks like as we're expecting. Perfect. As we can see, it has the alter table command in the up and revert code in down already created for us. All we need to do is run this script again. So back in our terminal, let's enter in npx TypeORM migration:run. And that's basically migration in a nutshell. In this lesson, we've managed to cover how to create migrations both manually and automatically with the power of the TypeORM CLI.